Hey everyone, and welcome to This Explainer. Today, we're taking a deep dive into a seriously mind-bending concept that's been making huge waves in the world of quantum physics. We are going to be exploring a theoretical structure that essentially attempts to completely rewrite how we calculate the fundamental interactions of particles. Now, I know that sounds heavy. It's a topic that mashes up high-level geometry with quantum field theory. But don't worry, we're going to break this whole thing down step by step to see exactly what all the excitement is really about. Okay, let's dive into this. When this concept was first dropped into the public eye in a major science magazine, it was described with this exact, incredibly dramatic phrase, a jewel at the heart of quantum physics. I mean, it sounds totally mysterious, almost mystical, right? And the media hype surrounding this was absolutely massive. It led a whole lot of people to basically imagine some magical, glowing gemstone just floating out there in the cosmos, holding all the secrets of the universe. But let's ground that hype for just a second. What are we actually talking about here? Well, the Amplituhedron is, at its very core, a geometric shape. More specifically, it's a mathematical tool. It was designed to make calculating particle interactions in quantum field theories much, much easier. It's basically a genius way to take these incredibly complex, headache-inducing physics probabilities and turn them into, well, questions of geometry. So here's our roadmap for today. First, we'll look at the messy math of particles. Second, enter the Amplituhedron. Third, from triangles to dimensions. Fourth, skipping space and time. And finally, a profound toy theory. All right, kicking things off with Section 1, the messy math of particles, and specifically, the problem with Feynman diagrams. For decades now, the standard textbook approach for calculating how particles interact, like, what exactly happens when two gluons smash into each other, has relied heavily on Feynman diagrams. And look, for really simple processes, they're fantastic. But there's a catch. The math literally explodes in complexity. If you want more precision in your answer, you have to add these things called loops, which represent virtual particles. So what starts as just a handful of diagrams suddenly balloons into hundreds and then thousands. It turns into these highly laborious multi-loop calculations that are just packed with severe gauge redundancy. And crucially, this traditional math requires you to hardcode two fundamental rules of physics right up front. Locality, which is the idea that particles only interact from adjoining positions in space and time, and unitarity, which is just the rule that the sum of all probabilities has to equal 1. Which brings us to Section 2. Enter the Amplituhedron. Let's clear up some myth versus reality. So when physicists Nima Arkani-Hamed and Jaroslav Trnka proposed this totally different geometric solution, places like Quantum Magazine reported that scientists had found the Amplituhedron. And honestly, that tiny word, the, caused a ton of confusion. The widespread misconception was that physicists had literally discovered one singular, giant master shape that somehow contained the entire universe and the whole history of time. But the reality? It's quite different. The Amplituhedron isn't a singular physical object you can hold. It's a mathematical concept that manifests in many different shapes, and each one of those shapes corresponds to a very specific calculation of a specific particle process. And this brilliantly illustrates the point using an analogy from a theoretical physicist's blog. Think about the phrase, the automobile. If someone walked up to you and said they invented the automobile, you wouldn't assume they built one giant, continent-spanning machine that picks up every single human on Earth at once to take them to work, right? You understand it's a broad concept representing lots of different individual cars and trucks. Well, the Amplituhedron is exactly the same thing. It's a class of geometric objects. If you have a specific number of particles and a specific number of internal loops that you need to calculate, you use a specific set of rules to build the exact Amplituhedron for that precise calculation. Moving right along to Section 3, from triangles to dimensions, let's trace the geometric stepping stones here. The original source paper brings us right back to the most familiar geometric object of all, the basic 2D triangle. In projective geometry, you can actually define the interior of this triangle by taking its 3 vertices and ensuring that all the coordinates that combine them are strictly positive. That simple, straightforward rule of positivity guarantees that you are looking at the bounded inside of the shape rather than the infinite, continuous space outside of it. Let's move ahead and see how this builds, because this is where it gets cool. If you can do this for a three-sided triangle, you can actually generalize this mathematical rule for a convex polygon with way more vertices. By extending this notion of positivity, which in math terms means using matrices with all positive ordered minors, you can rigorously define the bounded interior of incredibly complex multi-sided shapes, all without worrying about the coordinates summing to zero or somehow breaking the geometry. Now, what's really interesting is how this scales up. The physicists themselves sketched out what a three-dimensional face of a four-dimensional amplituhedron looks like for an 8-particle interaction. They take those simple rules of positive geometry from our basic triangle, they generalize them into something called the positive Grassmannian, and then project that into higher dimensions. And here is the absolute magic of this entire discovery. If you calculate the abstract geometric volume of this multidimensional shape, the resulting number is the exact amplitude, the probability of that specific particle process occurring. 0 Feynman diagrams required. The volume literally is the physics. Okay, section 4, skipping space and time. This is where we are truly shifting the paradigm. The advantages of doing things this way are just striking. First off, it's incredibly geometrical and honestly just really slick. Second, it has this huge sociological advantage. By phrasing complex physics problems as pure geometry, it basically opens the door and invites pure mathematicians to step in and help physicists solve problems, totally bridging those two fields. Third, it is highly efficient. What used to be a notoriously laborious multi-loop calculation can now, in many cases, just be done by hand using the volume of these shapes. But the fourth point, that's the most revolutionary one. To calculate the volume of this shape, you absolutely do not need locality and unitarity. And that is the crucial takeaway here. Locality and unitarity are no longer the starting point. Think about that. In the old Feynman method, you had to force the math to obey space, time, and probability rules at every single tedious step of the way. The Amplituhedron, it completely ignores space and time while you calculate the shape's volume. And yet, and this is the crazy part, when the calculation is finally finished, the final formula perfectly obeys locality and unitarity anyway. Those fundamental rules of the universe aren't inputs anymore. They just emerge organically as a byproduct of this positive geometry. Finally, section 5, a profound toy theory. It's time for a grounded reality check. So the crucial point we have to make is this. Right now, the Amplituhedron only works within a very specific framework known as planar n=4 super Young-Mills. Now, you definitely don't need to be a theoretical physicist to understand what that means for us today. It basically means this is a toy theory. It's a highly simplified, mathematically perfect version of reality that has maximum symmetry. So while it's very close to real-world gluon scattering, it is not the full, messy, chaotic reality of the standard model of particle physics. So crucially, Arkani-Hamed and his colleagues do not yet know how to apply this to other theories. It applies only to the planar part of this specific toy theory. Plus, at least as of the sources we are looking at, it doesn't give us any new hints about quantum gravity. This beautiful geometry works flawlessly within its own specific sandbox. But figuring out how to bring it out into the broader, chaotic universe, that's a puzzle that still remains unsolved. Which leaves us with this final, lingering thought. The Amplituhedron fundamentally proves that the deeply complex interactions of our universe can be rewritten as pure, elegant geometry, a place where space and time are just emergent illusions. But the big question remains, can physicists actually generalize this geometry to tackle the ultimate white whale of physics, quantum gravity? Or is the Amplituhedron, right now, just an excellently silly word for a beautiful mathematical toy? It is undeniably a profound first step, and the math is just gorgeous. But only time will tell if this jewel truly sits at the heart of all quantum physics. Thank you so much for joining me on this explainer, and keep questioning the shape of reality.